Hey there, in this video I'm going to walk through a factor analysis in SPSS. We're going to use the data from our factor analysis activity 1 here. We're going to use in this video the FA activity data set that's available on Canvas. And the instructions here tell us we want to conduct an orthogonal principal components analysis with the Varimax rotation using the following variables. So there are several groups of variables on the survey. One group, these success variables, sort of ask about your tools students use to be successful academically. That's those things about like their study habits or motivation, seeking tutoring help, stuff like this. And then there are several variables that are talking about like students' hindrances to their academic success. We could look at the variable, open up the data set, and kind of get an idea. So here are the 6 success variables. Using a tutor or study group will help me do well, and they'd respond to the items either strongly disagree to strongly agree. So it's a 5-point Likert scale. And then the hinder items are more about like your hindrances to success, like bad study skills will keep me from doing well. A busy schedule will keep me from doing well. So I'll just give you a kind of idea of the different items that we're looking at. So the first thing we're asked to do is to conduct a principal component analysis. And so the goal of a principal component analysis is really to reduce your variables into a linear combination of smaller components. We can kind of think of principal component analysis more as like a data reduction technique, and factor analysis is probably more appropriate when you believe that there is some latent construct that's defining the interrelationships among the items. So that's kind of 2 ways you can think about the differences between factor analysis and principal component analysis. 90% of the time you come to similar conclusions, whether you do it as a principal component analysis or as one of the many different kinds of factor analyses. And most of the time I'll tell you about which kind we're going to do. The fact that I'm calling it an orthogonal principal component analysis means that I don't want there to be a correlation between the components that you're extracting, which that's typically the default in principal component analysis. Is that the components are uncorrelated with each other. But in a factor analysis, you kind of have the option to do them orthogonal, where the underlying constructs that you're drawing from the data, that they are uncorrelated, or if they're oblique, that means that you're allowing them to be a correlation between the latent constructs. So just a little bit about the terminology right there. So the first question here asks us to address any assumptions prior to running the analysis. Addressing do we have an adequate sample size? Are there adequate correlations among the variables? So you'll find different kind of rules of thumb out there about sample size. And I've listed some in the course notes. And some of the readings give different recommendations. You'll see like just minimums, you need 200 people, 300 people. You'll see different like ratios. You need, 10 individuals per item that you're including in the analysis, something like that. I think a more, the larger the sample, probably the better. But I think this next part about adequate correlations also has something to do with it. the smaller the sample, probably the stronger correlations among the variables you need to be on the lookout for. So it's always a good idea to sort of assess the correlations among the variables. That's really what you're factor analyzing there, is the relationship among the variables. Normality isn't really an assumption for factor analysis. So the data don't necessarily have to be normally distributed in order to run a factor analysis. They really, it will help the factor analysis solution, but it's not necessarily a requirement. If you're doing a maximum likelihood extraction factor analysis, it does require multivariate normality. But like principal access factoring, principal component analysis don't require the data to be normally distributed. One thing to keep in mind is, so by default, the program will factor analyze the Pearson correlation matrix. And so, for Pearson's correlations, we're assuming that the variables are measured on a continuous or an interval ratio scale. So that's also something to keep in mind. We have a 5-point Likert scale, so it may be questionable whether or not we should factor analyze the Pearson matrix. Some people will see suggestions in the literature when you have Likert type data or like ordered categorical data, you should factor analyze a polychloric correlation matrix. But unfortunately, you can't get that out of SPSS. Outliers, I'm not going to be too concerned about outliers in this instance, just because our data are a 5-point Likert scale. Any response would be a valid response. Anything that's going to identify an outlier is someone who either set a 1 or a 5 on the scale, because everybody else, a few people were saying 5, everybody else was saying 1s or 2. It's going to say, if whatever we looked at z-scores or something, it's going to say that one's more than 3 standard deviations away from the mean. But to me, it's still a valid response, so I wouldn't be too worried about it. Multiclinearity. So multiclinearity isn't too big of an issue in factor analysis. We want our variables to be correlated among each other, because that means that they're all representing some underlying latent construct. But we don't want them, we're really looking for extreme multiclinearity. And this is where, perusing the correlation matrix will kind of get at that. If you see correlations that are like 0.9 or greater, 0.8, you might want to start flagging. That's saying that those two items are measuring the exact same thing, or measuring the same dimension of that underlying construct. If you have two variables are perfectly correlated, it's going to cause a problem for the analysis. Principal component analysis handles extreme multiclinearity better than some of the other factor analysis options. So it's just something you want to maybe be on the lookout for. But if you think of multiclinearity like you do in the regression sense, you don't necessarily need the variance inflation factors to be really small in this case. If they're a little high, it's okay, as long as they're not extremely high, like correlations around 0.9. So I'm going to open up my syntax file and kind of get an idea. We can run some of these and get an idea of how I'm doing this. So I'm going to open the data set. Here we go. I'm just going to run frequencies. It's always a good idea for any data analysis is to run frequencies on the variables you're going to include in the analysis, just to get an idea of maybe how the variables are coded. Is anything miscoded? Look here. Notice we have a 2, 3, a 4, some other random 4. What we have in here, if you can kind of double click on it and see, we have a couple people who are coded 4.14 instead of coded as 4. So we have several people who are miscoded, who have non-categorical values. Look, here's another one. You can double click on it. they're coded 2.91 instead of either 2 or 3. So we'd need to decide what we're going to do with these people. We could either round them into the nearest value. We could just delete those individuals who have non-categorical values. But we would need to decide what we want to do. We also get an idea here of like how much missing data there are. You can see item 1, 3 people are missing on it. Item 2, 1 person is missing, 1 person's missing. So you can get an idea sort of what's going on there. Here I'm changing the formats so we can display those decimals, so I wouldn't have to like double click on the item to look at it, and we rerun the frequencies, and you can see then there's the 4.14, the 4.37, 4.23. So you can see the actual values listed in the table. So that's just a shortcut. You can do that. Here I've decided that I want to recode them. I'll basically want to take the value and just round it to the nearest category and put the people in that category. I'm just saying that these were miscoded when we were typing it in. And so basically then this do repeat is just, it's going to repeat this command, anything between do repeat and end repeat. It's going to just repeat, replacing X with each one of these. So I'm taking each variable and then recomputing it by rounding the variables to the nearest whole number. We can run frequencies on it just to make sure that everything ran correctly. See, give it a minute to run it. Okay, so that took a minute to run, mainly because I'd also asked for some histograms in here too, to sort of examine, maybe how badly skewed the data are. So we can check our frequencies here, make sure, notice we don't have any non-categorical responses here on number 1 again, or 2. So our rounding syntax seemed to work. We could also, let's go back, what was it? It was a 4.14, there were 62 in there, so it should be 64 on our first item. We could come back and make sure 4 has 64 in it here. So that's one thing you would want to check to make sure it did it correctly. You go through there and check for all of the variables. We could also view histograms to kind of get a sense of maybe the normality of the data. They're all pretty skewed. Tutor doesn't, slight, a little less slightly skewed than others. Pretty normal. We can get an idea sort of the skewness and normality. Remember again, I'm not too worried about this because the data are a 5-point Likert scale, that it's not too surprising that the data are skewed. Here, missing data also doesn't seem to be an issue. Only 3 cases were missing, so I'm just going to ignore the missing data piece. Here's some syntax here if you wanted to check for outliers. Here again, I'm not too worried about it since the data are on a 5-point scale. Here I'm using, anybody's an outlier who's more than 3.29 standard deviations from the mean. I think that was Tabachnik and Fidel's recommendation. Do that, you basically just run descriptives on your items with the /save subcommand, and then you could run descriptives on then it puts in a new variable with the same variable name with a Z in front of it in the data set. And you can see, so you look at sort of the minimum maximum values here. So we have several minimum values that are that may be extreme cases, but you can see that these are mainly people who said strongly disagree on those items. Run frequencies on it, we could see that it's You can see here it's the people which strongly disagree, or actually disagree in this case. So here I ran both the z-score and the original variable so you can see which item it is. So for 2, if someone had disagree, where most of the people you see here are saying agree or strongly agree. Like I said, I'm not too worried about it because the data are like a 5-point scale. Checking correlations, just running correlations among the variables. We can kind of peruse the correlation matrix. What we're really looking for here is, say, you know, this the sex variable is weakly correlated with every other variable in the data set, then we might maybe exclude it from the analysis. The other thing you could look for is variables that are negatively related and maybe reverse code some of those. You could also do it if you had some variables, and I don't think we do in this data set, where the items are negatively worded. So where strongly disagree would be a positive thing. You could recode those before you run the factor analysis, but it's not necessary. So here again, we would mainly just peruse these correlations, just sort of making sure they were adequate, you know. And it looks like, you know, the success variables are more strongly correlated among themselves than they are to the hindrance variables, and those things, which is maybe actually a good thing if our survey was designed to measure 2 separate constructs. We would want the items in one construct to be highly correlated with each other, items of the other construct to be highly correlated with each other, and then them to be less related with items across constructs. If you want to check multilinearity, the best way to do it is using the regression command and looking at what are called variance inflation factors. And we'll talk about this more when we talk about regression diagnostics. I'll just run my syntax here real quick. Really, the only thing you're looking for, anything you want as a dependent variable, because variance inflation factors are only concerned with the independent variables in the model. And you're looking at these VIFs. If you see variance inflation factors that are, you know, 20, 30, I might be concerned that there's extreme multilinearity in the data set. Typically, we're looking for these to be, you know, less than 5 is typically ideal for regression analysis. Greater than 10 usually indicates there's some problem with multilinearity that you might want to be on the lookout for. You should have probably noticed if something's going on here, especially by perusing the correlation matrix too. But if any of these values are really, really high, you know, over 10, you might want to take a look at that variable and see what's going on. We'll talk about a little bit more about diagnosing multilinearity when we talk about regression diagnostics in class. So you run both a principal component analysis and a factor analysis in SPSS with the factor command. The only difference between a principal component analysis and a factor analysis in SPSS is this line of code. So the rest of it, if you're going to run a principal component analysis, you tell it that you're using your extraction method is PC, principal components. If you're going to run a factor analysis, you choose a different extraction method. Probably the most common is principal access factoring. So you'd put PFA. So that'd be a factor analysis using principal access factoring. There's also like unweighted least squares is another popular factor analysis extraction method. There's also maximum likelihood. Refer to the command syntax reference guide here for for more details on the different extraction methods available in SPSS. You can also review the class notes too for some details on the different extraction methods. So we basically list our variables, the ones we want in our analysis. This is telling us different things to print. We want univariate results, we want the initial results, we want the correlations, we want the KMO, we want the rotated matrix. And then here you put in the type of rotation you want. This is another part. So we say that we want to rotate the matrix using a Varimax rotation. And that's mainly just to help make the items more interpretable. You'll see the first, the unrotated matrix is going to look pretty ugly, and everything's going to seem to load highly on the first component. But we can rotate the matrix and make it more interpretable. I think Varimax rotation is a popular orthogonal rotation. You can look in the notes for different orthogonal and oblique rotations. And I printed out some pages from the PET book of where they discuss different rotation methods and when you might use different rotation methods. I typically default to like a Varimax rotation for an orthogonal rotation and an Obelman rotation or direct Obelman rotation for an oblique factor analysis. So we'll run our factor analysis syntax and sort of walk through it. So the first thing we get here are our descriptive statistics on our items. We see we had 197 observations in the sample. Remember, 3 people had missing data, so they were dropped from the analysis. Here's the same correlation matrix. I think this was actually a little bit easier to read than the standard one SPSS prints. So you can kind of peruse it looking for, making sure that there's adequate correlations. We also get the Kaiser-Myers measure of sampling adequacy and the Bartlett's test of sphericity. So the KMO here measures how well your data are suited for factor analysis. And, you can kind of interpret this as, the proportion of variance among the variables that might be caused by, say, the underlying factors. So it's saying that maybe, around 2/3 of the variance in the set of variables may actually be caused by, or could be attributed to the underlying factors that are driving these changes in these observed variables. You'll maybe even see this called like common variance, the portion variance in the variables that might be due to common variance among the variables. The Bartlett's test of sphericity, this basically tests whether your correlation matrix is different than an identity matrix. So an identity matrix has ones along the diagonal here and zeros on all the off diagonals. It's basically saying that there's no relationship among the variables. And surprise, surprise, it's different. If it's not, then it's saying that you really don't have anything going on here. You'd also have a really low KMO. You can look the Beaver's article on Canvas, and then in my notes there are different ways to interpret this. I think you usually want the KMO to be greater than, say, like 0.6, I believe. And then Beaver's gives different terminology for interpreting it, like meritorious, I forget, middling, I forget what all the different names they give. The next table are the communalities. This really the communalities here give the proportion of variance in this item that's explained by the extracted, components in this case. So we're explaining around 77% of the variance in this assessed one item that these components are. If we would have, in principal component analysis, if we would have extracted, or there are 12 items in here, if we would have extracted every item, then we would have explained all the variance. That's what principal component analysis is designed to do. But since we only extracted 3, we're only explaining, we're not explaining all the variance in the item. But that's how you interpret the communalities. So here's our variance explained, the total variance explained table here. So first thing it lists are your eigenvalues for each of your components. And so the eigenvalues here are variance components. So it's saying that component 1 is explaining around 3.5 units of variance in the total amount, in the total variation in this item set. So how much variation is in the item set? Well, that's equal to the number of variables. So there's 12 units of variance. So the proportion of variance explained here is just 3.5 divided 12. That's this 29% that they're calculating here. So the first component is always going to explain the most variance, and then the variance is going to drop off at each subsequent component or factor that is extracted. In our syntax, we told SPSS to extract any factor or component, in this case, that has an eigenvalue greater than 1. So you see that it extracted 3 components because only 3 components have an eigenvalue greater than 1. That's known as Kaiser's rule for selecting the number of factors. Currently, the optimal way to select the appropriate numbers of factors is, currently an unresolved issue in psychometrics. There's a lot of different recommendations for how to do that. There's a lot of, newer techniques people are very excited about. SPSS really only offers the Kaiser rule, the minimum eigen rule, and then the scree plot here. In the scree plot here, it basically graphs the eigenvalue on the y-axis, and then each component on the x-axis, and you look for the bend in the curve. Like, where does it kind of start to flatten off? It really starts to flatten off here about the 4th component. So this would say you'd either extract either 3 or 4 components. There's another thing called a parallel analysis that we're not going to get into because SPS didn't offer it by default. You can also, I think another way of extracting factors is, we want to extract, we could look at whether a 3 or 4 factor solution makes sense in this case based on whether the 3rd or 4th component we extracted is meaningful or not. So maybe we can extract all components that are actually, substantively meaningful. So you can compare a 3 and 4 factor solution to see, is the 4th factor even meaningful if I extract it. We typically also want to look at the proportion of variance explained here, because it also gives a good indication of how well the extracted model, how well it's performing, for lack of a better term. Typically, you'll see recommendations throughout the literature saying, you should try to extract between 50 and 70% at the minimum. I've seen other people make arguments that, well, in the social behavioral sciences, our measures are a little more messy. Our measures are more abstract. Explaining 50% of the variability in the item set is a good goal to achieve. And I think that's what the Beavers article kind of argues for too. So explaining around 60% of the variation in the item set, I would say is pretty good in this case. Let me switch back to the to the syntax. This is where you change the extraction criteria, you know, how many factors that you want to extract. The min eigen 1 right here says that I want to extract all factors or components with a minimum eigenvalue greater than 1. You could change this to a 2 and you'd extract any eigenvalue that was greater than 2. You'd extract any components that have an eigenvalue greater than 2. You can also force a certain number of factors. So say we wanted to keep that 4th factor, we would just type in here factors and then in parentheses 4, and that's going to say we want to force it to extract 4 factors and give us a 4-factor solution. So that's how you change those two, the number of factors extracted. Here's the unrotated matrix. We're going to ignore it for now. Here are our reproduced correlations. So these are the correlations that are implied by the factor structure that we've extracted here. The residual correlations then is the difference between our observed correlations and the correlations implied by our model. What we want to do here is look for large residual correlations. Here it gives you a little footnote here. There are 36 residuals with absolute values greater than 0.05. That's around 54% of the data. And, you can see here's a couple that are sort of large. I'm not doing a good job of explaining the relationship Hinder 6 has with several other items you can see here. I think some different rules of thumb. I think Field in his stat book says that his rule of thumb is that you want your residual correlations at least 50% of them to be less than 0.05. You can also look for what proportion are greater than 0.01 as well to sort of highlight the larger residual correlations. The idea is if the residual correlation is less than 0.05, that's saying that there's essentially nothing left there. And that's good that we're explaining that our model's in explaining all of the relationship between that variable and the other variable. Our rotated component matrix is what we'll want to look at here for the principal component analysis. This is how we define our factors or components in this case. So sort of the first thing I'll look at in here, we use this matrix to sort of define our components, but also you look for items that cross-load onto more than one factor component. Ideally, we want items that load highly on one factor or component and load weakly on the other two. In our syntax, we ask SPSS to suppress any loadings less than 0.32, so that's why these are blank. This item loads on all 3 components, but the loading on component 1 and 3 is less than 0.32, so SPSS blanked it out for us. You can change that and this part of the syntax. If you want to blank out any correlations less than 0.4, you can do that as well. So we looked at this Hinder 6 test anxiety will keep me from doing well. Seems to load on both component 1 and component 3 at about the same the same strength on each one. I think Tabachnik and Fidel give a rule of thumb that they look for if you have a variable that cross loads on more than one component, if it loads more strongly on one component than another, and they define that as 0.2 or larger. So if this was 0.7 on component 1 and 0.49 on component 3, we might keep this variable with the first factor and say that it loads more strongly on it. So in this case, I might actually remove this variable. I'm going to take this and copy it to an Excel file here so I can compare these results with when I remove the variable, what it looks like. That doesn't look good either. So we're going to remove let's remove the Hinder 6 variable and rerun the factor analysis and see how the solution changes. If the solution changes drastically, then it's saying something else is going on. But if our solution remains pretty stable, then we've probably achieved a satisfactory solution for our factor analysis, and we can proceed with naming our 3 components here. So basically, to run this, all we need to do is just remove Hinder. We could copy this syntax, same syntax we used before. I'll copy it. And just remove Hinder 6 from the list. Rerun the analysis. Well, let me change this back to, we were selecting minimum eigenvalues greater than 1. Here we go. Notice we still have the same number of people, 197. The correlation measures stay mostly the same. You know, we're just missing a row that we had before. Your KMO will change slightly, and your Bartlett's test will change slightly because we're analyzing a different correlation matrix here. Your communalities may change slightly too, but they're all pretty strong. Success 4 is actually kind of low here. So only around 20% of the variation in success 4 is being explained by the extracted components. This was pretty similar to what we had before as well. You see, we're still extracting 3 components with eigenvalues greater than 1. The fourth component eigenvalue dropped some. We're now explaining around 62% of the variation, slight increase than what it was before. The scree plot still suggesting around 3 or 4 factors, really flattens off right here, that I might go with 3 components. Ignore the unrotated component matrix. We can look, kind of peruse these residuals. Remember, we noticed the Hinder 6 item had large residuals last time, and it also had that cross-loading. So having some large residuals here for success 3. Remember, we weren't explaining a lot of variation in it, and that variable as well from the communalities. But we can also then we can also look at our rotated component matrix, kind of get an idea of, we can look for cross loadings here. It doesn't look like any variables loading, cross loading on any of the other components, at least not to an extent greater than 0.32. We might go ahead and proceed with maybe starting to name our components in this case. Let's start with component 1. So bad study habits will keep me from doing well. A dislike of this topic will keep me from doing well. A busy schedule will keep me from doing well. Not enough practice will keep me from doing well. Not going for help will keep me from doing well. Maybe we'll call these something like success hindrances, stuff that will keep me from being successful. And all of the loadings here are all pretty strong too, 0.7 to 0.5, which are pretty decent loadings. The second component, good study habits will make me do well in the scores. Being motivated and determined will help me do well. Regularly attending class will help me do well. Maybe we could call this like positive success habits. And all of the variables load onto this component very strongly here. The third component, professors, teaching style effects, how well I do. Using a tutor or study group will help me do well. Having a peer mentor will help me do well. Maybe these are like mentoring relationships or mentoring habits. Two of the items load pretty well on this construct. The success 4 item loads pretty weakly, really borderline here. It's less than 0.4. We also saw that the success 4 item here has some pretty large residual correlations, and and has a really low communality. It might suggest this item is also we're not explaining variation in this item very well, that it's sort of weakly related to this construct. Some people may say it's kind of iffy to have a 2 item construct. We'll check out the reliability of this item, of this scale, then check out the reliability of this scale to assess, is it worth having the 3 item or maybe a 2 item scale? So that's sort of the thought process you go through. You look at which variables are related to that component to think about, okay, then what might this component or underlying factor be? And a lot of times beforehand, you sort of maybe designed your survey to measure certain constructs. So you're wanting to be sure that the items you designed to measure, say, success hindrances, all of these items are measuring that, if we measured all these success items to represent something like academic successes, they're breaking out into 2 separate components, then, we didn't measure maybe that construct we were trying to develop as well. It seems like we're measuring like success hindrances and like mentorship habits or something here with components 2 and 3. So after you run a factor analysis and you've decided on your final factor solution, you have what they call, they've achieved a simple structure where each item loads highly onto one component and weakly onto the other components or factors like we have here. We'd want to also assess the reliability of those scales. And we assess reliability in SPSS, or maybe really the most common way to assess reliability is using the internal consistency reliability alpha or Chromebox alpha. You can get that in SPSS through analyze, scale reliability analysis here. Or here's some syntax for it. Actually, I don't think you need these. You basically, reliability, give the variables that are in the scale. You can name the scale, give the scale a name here. We want to compute Chromebox's alpha, and then we can get some descriptive statistics, information about the item, some summary statistics here. And we want to do that. We'll go ahead and do that for all 3 of our scales. Where'd it go? Did it run it? Just run it again. Here we go. So we look for our first scale, success hindrances. We get a Chromebox alpha of 0.75, which is pretty decent. Usually we want these to be greater than 0.7. Greater than 0.6 is borderline. It's probably okay. Less than 0.6 indicates not very good reliability. It computes the Chromebox alpha on the raw data, and then if we standardized all the items, This would be good if your items were measured on different scales. You'd want to standardize them before you did that. Also, if some of your items in the factor analysis, if we noticed, if you notice in the factor analysis, like some of the items loaded negatively on other items, we'd want to reverse code that item before we put it into the factor analysis. Before we put it into the reliability analysis. You'll see that on the second activity. We'll have that. So we'd want to reverse code the item. Here we go. Where's our? Which ones? It's the positive success habits. Has a pretty strong reliability, 0.86. Here, so it's pretty good reliability. This would be the other table I would look at. This tells you what happens if we delete one of those items. It gives you the Chromebox alpha, what the Chromebox alpha would be if we deleted that item. This item already has great reliability. It's only 3 items. I would really be hesitant about deleting an item. And you can see that if we deleted an item, it would reduce the reliability of the scale. Another important thing to maybe look at here is this corrected item total correlation. So this gives you the correlation between the item and the scale with that item removed from the scale. So if it was just a scale with just these 2 items, so the idea is if that item was a good indicator of that latent construct, then it should be highly correlated with a scale based on other items made on that construct. So you'd want to see high correlations here as well. We can look at the same thing. So this was our mentorship habits. It has a borderline, sort of a weakish alpha, probably not too bad, but not great either. Let's see if we can improve it at all. Notice if we delete the success 4, our alpha jumps dramatically, right? About 0.8 or 0.79. So that's, so now we have to think, do we want to have a 3-item scale with weak internal consistency reliability? Or do we want to have a 2-item scale that has a decent internal consistency reliability? You'll see all kinds of stuff in the literature, about people advocating against the use of 2-item scales. I see it done in real life all the time. People publish on 2-item scales. I think I would be more concerned with keeping this item in there. It had a weak factor loading, like what was it, 0.34, 0.35, and also had it also has a weak correlation with the item compared to the scale without the item in it, especially compared to the other correlations of the other items. That the big increase in the alpha might convince me to go with a 2-item scale in this case. So we could do the same thing for the last item set too. We had an alpha 0.75. Deleting an item really wouldn't improve the alpha. We could delete hinder 3, get a modest improvement in our alpha. We'd probably want to make a judgment call about whether we think we should keep this item or not. It doesn't really hurt anything to keep it, but it's not really adding too much to the scale anyway. It works pretty good without it as well. So you can make a judgment call there about whether you keep or not keep that item. I would kind of think about the theory underlying this topic. Does that seem to be a really important dimension of that construct? If it is, I would probably keep it. If not, then you might have some justification for removing it as well. One thing I just thought about that I forgot to you know, when we deleted Hinder 6 and we ran our factor analysis, I remember I pasted the original correlation matrix in Excel. We could do the one without Hinder 6, and you might want to just go around and just compare. If you notice, the factor loadings change, but they only change slightly, and the same items tend to load on each one of the scales. The loadings change somewhat, but not too dramatically. If we look at these two here, so I would say that we reached probably a stable solution to our factor analysis. I just realized I forgot to do that part. So that's pretty much our a brief walkthrough through factor analysis. You can see my syntax posted on Canvas. You know, how you could create component scales using the mean.x function. You know, since our Hinder had 5 items, we would say we would create a scale called Hinder where we would average across those 5 items. Same thing for success habits and mentoring habits. You can see here, so here's factor analysis syntax with an Oblman rotation. Notice the thing that changed was the extraction. I'm doing a factor analysis using principal access factoring, and I'm using an oblique Oblman rotation here. The other big difference between, the main difference between an orthogonal and oblique rotation is you are going to have your rotated factor solution is going to be broken up into 2 separate tables. There's a pattern matrix and a structure matrix. And you'll want to use sort of both matrices to sort of decide kind of what's going on in your analysis. So the pattern matrix, you can these would be your factor loadings, or what we typically consider our factor loadings in this case. Most SAS programs give you the pattern matrix by default. SPSS gives you both by default. The loadings in this table are more like standardized regression coefficients. So it's a relationship between that variable and the factor controlling for all of the other variables. Typically, the pattern matrix is a lot cleaner, as you can see here, not as many cross loadings. The structure matrix is the simple like bivariate correlation between that item and the factor. And so the more strongly correlated the factors are, the bigger difference you'll find between the pattern and the structure matrix. In the literature, you'll get different recommendations. Tabachnik and Fidel suggest just interpreting the pattern matrix. It's easier, cleaner to interpret. In their factor analysis book, PET suggest using both matrices and reporting both, especially if there's a strong correlation between the factors. It suggests naming your factors based off the structure matrix. You know, here we kind of, you know, maybe use a congruence between both of these. You know, it looks like, you know, success 4, professor's teaching style affects how well I do in this course. Maybe the item that had the low reliability before, that caused that scale to have the low reliability rather, doesn't even have a factor loading greater than 0.32 on any of the items. We can look at same thing in the structure matrix, the correlation, and even there we might want to might consider dropping that item. Same thing with Hinder 6 here. It has relatively similar correlations across 2 factors, and you know it's relatively weak on the other the factors it's loading on compared to the other items in those scales. Same thing you can see here. So we might take this, incrementally first, drop success 4, run the factor analysis, see how that affects the hinder 6 variable, and make our assessment there. But the big issue is that to notice that what the difference between the two matrices are. And so this is only, if you do a factor analysis with an oblique, with an orthogonal rotation where there's no correlation between the factors, you'll only get one rotated factor matrix. It's only when you have an oblique rotation where you're allowing a correlation between the factors that you'll get two separates, the pattern and the structure matrix. I supplied a little note on Canvas that gives more detail about these two. So if you look on Canvas, there should be on there a note on the difference between the pattern and structure matrix. So I'll go into a little bit more detail about them, and then give you the citations from Pat and Tabachik and Fidel about which to use. I tend to try to use both to sort of make a decision about what's going on. And then if there are drastic differences between the two, and that will occur when there's a strong correlation between the factors, report both matrices in your output. If there's not a strong correlation, you can probably get away with just reporting the loadings from the pattern matrix. So that is our quick intro into factor analysis. As always, if you have questions or concerns, please shoot me an email or post something on the message board. Thank you.